Today lecture we're gonna learning about the electromagnetic spectrum. So we're gonna start where we end up last time with the electromagnetic wave. Just a quick reminder: the electromagnetic waves, when created by electrical field and magnetic field, they are traveling in a certain way, and they are perpendicular. And to see or to imagine how that work, to be able to just can you imagine how the electromagnetic wave created. Let's start with a simple example here. We have the simple antenna, which basically the antenna is a piece of metal or wires, and with the source for the current, or is the isolated current, or it's called the AC current. It is waving or the isolating. So based on that, based on the positive and negative charge directions, to create electromagnetic field pointed up. And since the source will be isolated, so the same thing, the electrical field will be isolated. And then keep isolated, even change the polarity, positive to the negative in other directions, meaning they're gonna be change the direction of the electromagnetic field as well. So doing that, we create the shape of the electric field pointed up and down based on the direction of the source. By keep doing that, you end up with that wave, what we call it about the wave, or the electric waves, or electromagnetic wave. Similarly, to keep imagine what the magnetic field came from, since we have the current go through the wires, that the wires will be generate a magnetic field. And the magnetic field can be found based on the right-hand rules. And based on hand rules will be find the magnetic field will be point right or left based on the direction of the current. Since this the current will be AC, will be isolated. So the change of the magnetic field directions will be pointed right or left. So based on that, we create the magnetic field right or left. So electromagnetic field, if you combine those two images together, that's the electromagnetic field how created. Now, regarding for the electromagnetic wave spectrum, before we start to that, just a quick reminder some terminology that we covered last time, and basically talks about the wavelength. And the wavelength based in our wave, electric wave or magnetic wave, that's the wavelength, the space between two peaks. And we missed the last time about the relations between those, the frequency and the wavelength and the speed of light. So they are in one single formula here. And since the speed of light is constant, so the magnetic field or electromagnetic field spectrum can be represented by lambda or f. So basically what that means, if you are given the frequency, I am able to use this formula to calculate wavelength, and vice versa if I given lambda, so I can find the frequency. So basically the spectrum of the EM wave can be represented by wavelength or by the frequency. Since you can, but any certain point, you can find either way if you are given one. So here, regarding for the spectrum, so the spectrum usually is listed by frequency or lambda. Here, the top one listed by lambda, and the below one listed by the frequency. And most familiar one and common one we call it by the frequency sometimes really. For example, if you're looking for the AM, your radio antenna, you mentioned about the number with the frequency, the hertz, megahertz or something. FM similarly, okay? So, but anytime we can find the wavelength. Okay. So the spectrum can start from the zero, from the low frequency to the high or very, very high frequency. And every certain range of the frequency, it has same properties. We focus it or we name it as the one name. And similarly, that the division or that spectrum can be represented by the wavelength. For example, here is that we have the radio wave in certain range for the frequency with the same one on the lambda. We have a radio wave, and that range can you use for the radio wave, like the transmitter radio or TV or any other communications systems. And then if you increase going to back in your spectrum in that directions, you increase the frequency and you increase the lambda. Now the spectrum go to the another area, what we call the infrared. And then move more, it give you the ultraviolet ray, and so forth, X-ray, gamma ray. So depending about where your range, you have magnetic or electromagnetic field, it has wave, it has certain properties. So let's start with the first one here, with the radio waves. And if you see that radio wave, it's the range around from the 1 mega to the 1000 or the 100 megahertz. That's what we call AM. An application for that, we have the AM radio. If you look at the your radio, you will see the range of the your radio between 80, 90 megahertz to the 106 megahertz. So that's your electromagnetic field. That's your AM wave travel out of the air, or your radio channel transmitted their program or their signal through that particular range. Okay. Again, increase the frequency, all the time it change the spectrum of the wave. So here is an example for that. So in your cell phone here, so we have the antenna, and the antenna, it can be calculated based in the operating frequency of your cell phone. For example, here we have the cell phones usually work. This is what we call GMC, Global Mobile System. And here's the frequencies 850 megahertz. And usually the antenna length or the antenna size given by a half of the lambda. So the antenna size would be half of the lambda. And sometimes given even smaller than a quarter of the lambda, but not smaller than that. And if you look at if you want to calculate how much I have length for my lambda, for my antenna here, so we have to calculate our lambda first. Since we are given the frequency, so we can find our wavelength. So wavelength, in that case, will be speed of light divided by the frequency. And we have speed of light is constant. And the frequency depends about your operating. And in this case here, I have 870 or so mega, by the way. So again, as a quick reminder, a hertz, as we mentioned last time, it is 1/2. So inverse of time, 1/2. And megahertz here, basically 10 to the power 6 a hertz, or 1 of the time. So I have here is the mega, so basically mean power to the 6. It's type it 1/6 or a hertz. So here the second will be cancelled second. So we end up with the 0.35 meters. Now, regarding for the antenna, so here is the, sorry about that. Here is the antenna size or length. Lambda/2. So in this case, I end up with the 1.7 meters. If you want to change it to the something we're familiar here, it's close to the 7 inch. So the 7-inch, it is the size of my iPhone. So in the cell phone here, if you open it from the inside, so here is the antenna that's located in data place. So for example, when we have the new application like 5G, for example, 5G, it has smaller antenna. Smaller antenna means less than 7. What's that mean? If you look at the formula to find the lambda, which function with the antenna, it means more frequency, higher frequency. So higher frequency, that's what led me to I can reduce the size of antenna. So this is the radio frequency application or range from the AM. Let's move for the another spectrum, what we call the microwave spectrum. The microwave spectrum starts from the gigahertz, which is a very high frequency. And generally speaking, you can find many applications for the microwave, like radar, or what we have here in very close applications, a microwave we use for a heating here. So for heating here, if you have given example here, typical microwave operating for the microwave oven, we have the frequencies 2.5, 2.45 gigahertz. Again, for the gigahertz, it means power to the 9 hertz. So I can find out how much the wavelength we have in that case. Speed of light divided by the frequency of the wave. And we have here's meter per second and divide by 2.45 power to the 9, 1/2. And if you calculate this one here, you end up with the, sorry about that, you end up with the value 12 centimeters, or we can say 12 centimeter here, 12.2 centimeter. So what that means here, 12 centimeter as a lambda. So in microwave, if we imagine it as a standing wave, it is 12, and the lambda it will be 12 centimeters. What that means for your microwave, your wave will be travel inside your microwave as standing wave. With the lambda, it is 12 centimeters. You can measure that, if, for example, if you put the piece of chocolate in your microwave and you heat it, and you can see what the point is that in your chocolate heated is 2 points here. And basically what we have here is the half of wavelength. So it's half of 12 centimeters. That's the place where we, so that's why in microwave, you see a piece of the rotations. We put the food inside and that keep rotation just to across the microwave side or microwave, ascending microwave, and heated all the parts around that situation. Keep moving in the EM wave spectrum. Now we're moving for the infrared light. So the infrared light, it is generally produced by the terminal motions of molecules, or usually for a heating. So basically what that means, so basically what that case is talking about the infrared, which located in below of the red wave. So that's why infrared means below red. So another one here, for example, what we call the visible light. So visible light starts from the range between 750 nanometers as a red to the 400 nanometer for a violet. So if you need to calculate what the wavelength for both of the red and violet red, that's located as the range of your visible light. So here is the formula that we're gonna use, C lambda C over F. If you use this 7.750, so we calculate that one, you will find it is 4 power 14 meters, and this is one for red. You can calculate similarly for the violet. That's another range. So let's move another range beside the infrared and violet. So here is the X-ray. X-ray light, which has the more high frequency. An example for that, basically what we have, it is more or smaller wavelength, larger frequency. So larger frequency, more speed for my wave. And for the X-ray, it has more speed and more energy. It can be penetrated your body and take a picture for the bone or anything inside the body, that as we see for the X-ray. So that's one application. When you increase the frequency or decrease the wavelength, so that our wave, it has a more powerful and more ability to penetrate stuff. So for the X-ray specifically here, and some of them penetrate, they are healthy, it's not gonna hurt like the X-ray, but the ultraviolet, this one is the unhealthy, so we gotta cut the radiations in that case. So let's say example for our X-ray, we have the wavelet this time. We're given the wavelet and what the frequency for this wavelet for the X-ray. So again, we have the common equations. So I can find, this time I am asking to find the frequency, not the lambda. So the only change here, the C divided by lambda. All the time C is constant, power to the 8 meter per second, divided by 0.01 nano, which means here is the nano, means power to the -9. Here is the meter. So the meter, we cancel with the meter, you end up with the 1 over S. And that value 3 power to the 19, 1 over S, or 3.0 power to the 19 hertz. So it is very high frequency that is. This kind of the application for the electromagnetic wave spectrum.